everyone, today we are going to learn about exponential decay. We're going to learn how to graph exponential decay functions and use exponential decay models to solve real-world problems. Before we get started, I would like you to please factor these two expressions. The first expression is x to the fourth power minus 18x squared plus 81. And the second one is 15x to the fourth power minus 12x to the fifth. I want you to factor each of these on your own by pausing the video, and when you are finished with factoring each, I want you to restart the video and we'll see how well you did. All right, let's go ahead and factor these. So the first thing that we want to do is we want to recognize that this problem is in quadratic form. And better yet, this is even a perfect square trinomial. But let's say you didn't see that this was a perfect square trinomial and you simply broke it down into two parentheses. We would have split apart the x to the fourth into an x squared and an x squared. And we need to figure out what two numbers multiply to equal 81, but together add to equal negative 18, and that's a minus 9 and a minus 9. So you could write this as x squared minus 9 squared, which is a perfect square trinomial. But beyond it being just a perfect square trinomial, we have ourselves double dots. X squared minus 9 is a dots, and x squared minus 9 is also a dots. So I'm going to rewrite this as two parentheses times two more parentheses. So this is going to be x plus 3 times x minus 3, x plus 3 times x minus 3, and we have two x plus 3's and we have two x minus 3's, so our answer is going to be x plus 3 squared times x minus 3 squared, and that is our answer. So that one was a little bit complicated, but kind of cool at the same exact time. Hopefully you did okay, or at least was able to get pretty close to what the answer actually is. Let's go ahead and look at number 2. For number 2, whenever you see two numbers or two terms, you want to look for one of two things. Number 1, you want to look for dots, or difference of two squares. In this case, 15 and 12 are not perfect square numbers. So that means you look for the second thing, and the second thing is a greatest common factor. 15x to the fourth and 12x to the fifth, both of these two terms have in common a 3 and an x to the fourth. The smallest exponent is 4. So this is going to be equal to 3x to the fourth power times 3 times 5 is 15, and I took away the x to the fourth, so I have 3 times 5 minus 3 times 4x would equal 12x to the fifth. So we have, our answer is 3x to the fourth times 5 minus 4x. Now, if you recognize that this was not written in descending order and you wanted to rewrite this as negative 12x to the fifth plus 15x to the fourth, and you factored out a negative 3x to the fourth, that would be fine as well. Your answer would now be 4x minus 5 inside of the parentheses. Both answers would be absolutely correct. All right, so hopefully factoring was okay for you. We will have more factoring practice coming up, but here are our learning targets for today. Our learning targets is I want you to be able to say that I can graph an exponential decay function using a parent function, reflection, stretch, shrink, translation table. I also want you to be able to say I can use exponential decay models to make predictions about real-world occurrences. So that should be predictions about real-world occurrences. We have a couple more vocabulary words to help us with this unit. And that first vocabulary word is an exponential decay function. An exponential decay function looks like an exponential growth function. It's going to be in the form of y equals a times b to the x. A, once again, is going to be greater than 0, or a positive number. And our b value this time is going to be in between 0 and 1. So what you're going to see is you're going to see a small number. Typically, that number is going to be in the form of a decimal or a fraction. And that decimal or fraction is going to be a number that's in between 0 and 1. So it won't equal 0 and it won't equal 1, but it'll be a smaller number. And whenever you have a b value that's in between 0 and 1, what we end up getting is a b value, our base value, becomes a decay factor. So in the past, when b was greater than 1, b was our growth factor. Now, in any function written in the form y equals a times b to the x, our base now becomes the decay factor. Once again, we call that our multiplier. It's the number that we're multiplying each time in order for you to get the next number or to get our next value on the graph. So if you see a decay factor, you're essentially going to be looking for your b value. So the parent function for an exponential decay graph is going to be a reflection of our exponential growth graph. The reflection this time is actually going to be a reflection across the y-axis. So in our last function, all of our functions, we started where our flat part was on the negative side and then it increased going up. And now we've essentially reflected that graph across the y-axis. So the function f of x is equal to b to the x, where b is a number in between 0 and 1, is the parent function for the family of exponential decay functions with a base of b. The general shape of f of x is equal to b to the x is shown below. We will have an asymptote just like we did before. It will be a dashed line once again that's horizontal and located at y. This is at y equals 0, and that 0 comes from your k value. So y equals k is going to be our asymptote. So the domain of y equals b to the x is still going to be all real numbers. Our range is going to be y is greater than 0, and our asymptote is going to be y equals 0. And once again, those 0 values come from our k value. So we will still be working with the function y is equal to a times b to the x minus h power plus k, where a, b, h, and k still follow the same exact rules as what we've had before. In addition, what's really nice is that the parent function goes through 0, 1, 1b. So that means that our parent function is still going to be 0, 1, and 1 comma b. So that's the exact same structure as what we had for exponential growth. The difference is the shape of the graph. Whenever we have a b value in between 0 and 1, our shape is going to be a reflection across the y-axis. Now, if you do end up with an a value that's negative, like in letter A, we would still end up with a reflection across the x-axis, and we would still have the same transformations as what we've had in the past. So for letter A, we're still going to be identifying our same information just like we did with our growth models. We have our a value is going to be equal to -2. Our b value is going to be equal to 4/5. We're not adding anything in the exponent position, and we're not adding anything outside of the problem, so our h value is going to be 0, and our k value is also going to be 0. So that's going to help us to create our table. And before we are finished, we will still need to identify what our domain is going to be, what our range is going to be, and what our asymptote is going to be. So I'm going to start off with parent function. My parent function is going to be 0, 1, and then 1 comma, my b value is 4/5. So I'm going to write that as 4/5 to start. And if I end up with a funky fraction at the end, I'm just going to change it to a decimal because decimals are easier to graph. Reflection. In this case, our a value is negative. So that means I'm going to take all of my y values and multiply it by -1. So I'm going to have 0, -1, and 1 comma, -4/5. Next, we have stretch shrink. And in this case, the absolute value of -2 is equal to 2, and that's what I'm going to multiply all of my y values by. I'm going to multiply all of my y values by 2. So I have 0, -2, and 1 comma, this is going to be -8/5. We're not adding or subtracting anything, so we have no translation. So these are the ordered pairs that we're going to plot. The issue is -8/5. Nobody really knows what that is, so put that into your calculator. -8/5 is actually -1.6, and -1.6 is actually a lot easier to graph. So that's going to be the ordered pair that I'm going to graph instead. Before I do that, I'm going to identify my domain, which my domain is going to be all real numbers, and my range. Since I do have a reflection, that automatically means I'm going to have a less than. So if you have a reflection anywhere in your problem, you'll have a less than as a part of your range. Y is going to be less than our K value, and our K value in this case is 0. So Y is less than 0, and my asymptote is at Y equals 0. So I'm going to graph my asymptote first. It's always important that you graph your asymptotes. I'm going to be looking for that on all of your tasks. Next, I'm going to plot 0, -2. So here's 0, -2, and 1, -1.6. So that's going to be about right here. And our graph is going to be going through these points, and it's going to be approaching the x-axis, or approaching our asymptote. And then it's just going to be like a sideways J. And then that's going to be our answer. So it's going to be like approaching the asymptote. So it's going to be kind of like a curve that's approaching. We always start at our starting point and then go through the next point, and then we just continue. And that is our graph. Let's go ahead and look at B. For letter B, the first thing I'm going to do is identify what my A value is. It's 3. My B value is 2/3. My H value, it's the opposite of what I see in the exponent position, and the opposite of a +1 is a -1. And our K value is exactly what we see, so that's going to be -3. Now I'm going to create a table of values. Create my table, set it up. And my ordered pairs are going to be 0, 1, and 1, comma, my B value. My B value is 2/3. So I'm going to work with 2/3 until I get to the very end. And then if I end up with funky fractions, I'll change it to decimals because that's easier to work with. In this problem, my A value is not negative, so I will not have a reflection across the x-axis. My stretch, well, in this case, the absolute value of 3 is 3, so I'm going to multiply all y values by 3. So I have 0, 3, and 1, comma, 2 times 3 is 6. 6 divided by 3 is 2. So I have the ordered pair 1, 2. For translation, I'm going to take all of my x values and subtract 1, and I'm going to take all of my y values and subtract 3, and that comes from my h and k value. So I'm going to have -1, 0, and 0, 2 minus 3 is -1. So these are going to be the ordered pairs that I'm going to plot. But before I plot them, I'm going to identify what my domain is going to be, my range, and my asymptote. My domain is always going to be all real numbers. My range, because there is no reflection, we're going to have y is greater than, and it's going to be y is greater than my k value. And my k value is -3, so my range is going to be y is greater than -3. My asymptote is always a horizontal line for these types of functions, and it's going to be y is equal to my k value, which is -3. So I'm going to go down to where -3 is, and I'm going to draw a horizontal line. 1, 2, 3. This is my asymptote, and I always need to draw the asymptote. That's going to be something I'm going to look for. And I'm only going to plot 0, -1. I'm sorry, -1, 0, and 0, -1. So we have -1, 0, and 0, -1. So going through those points, it's going to be approaching my asymptote. And it's going to kind of come down like a stretched out C or an elongated L, whatever way that you want to look at it. It's supposed to be like a curve. So hopefully you did okay. Those graphs make sense to you. And if they don't, please feel free to let me know. Email me. Let me know next time I see you in class. All right, here we go. We are going to now transition to exponential models and how to identify pieces of information based on an exponential decay model. We have ourselves a new formula that you will need to know. So it says when a real life quantity decreases, so you're going to see language that's going to say decreases, or you'll see other language that'll declines, a population declines, or goes down. You'll see some kind of language that indicates that something is going down. So when a real life quantity decreases by a fixed percent each year or some other time period, the amount y of the quantity after t years can be modeled by the equation y is equal to a times 1 minus r to the t power, which is something that you'll need to memorize. So for our growth model, in the last lesson, when we were talking about problems that do not deal with interest, so this is not interest problems, we had y is equal to a times 1 plus r to the t power. Now we're talking about decay problems. And the only difference is that now we have y equals a times 1 minus r to the t power. So the only difference is if you're talking about growth, you'll have a plus sign. If you're talking about decay, you'll have a minus sign. And you'll have to look for context clues to tell you what formula you're going to use. A represents your initial amount. It's how much you're starting with. R represents your percent decrease that we always express as a decimal. And 1 minus r represents your decay factor. This is something that you're going to see in your homework, so please make sure that you pay attention to what the decay factor actually represents. So let's look at number 2. In example number 2, it says, a new television costs $1,200. So we start off with the television equaling $1,200, so that's going to be our A value. The value of the television decreases by 21% each year. That's going to be our R value, and we always represent it as a decimal. So that's going to be 0.21. A way, if you ever get lost about how to change something from a percent to a decimal, just take your percent, divide it by 100%, eliminate the percentages, and 21 over 100 is 0.21. You would just put that into a calculator and come up with your answer. But that's the way how do you transition from a percent to a decimal. So we're going to write an exponential decay model. So we're going to write our function without having any specific number of years. So we're going to let t equal t. T is not going to equal anything quite yet. So our exponential decay model is going to be written in the form of y is equal to 1,200 times 1 minus 0.21 to the t power. Or we can write it as y is equal to 1,200 times 0.79 to the t power. I think that the best way to write it is as simple as possible without that minus sign. So what you're going to see is a decimal that's going to be less than 1. If you ever see a decimal less than 1 inside of that parentheses, that indicates that you're talking about decay or decreasing a decay model, an exponential decay model. Now it says estimate the value after 2 years. So now we're going to let t equal 2. So I'm going to write y is equal to 1,200 times 0.79 to the second power. And all you have to do is put that into your calculator exactly as you see it. I would recommend that you use parentheses and all. And when you put that into your calculator, you're going to end up with 748.92. And we're talking about the value of a television, so that's actually going to be in money. So now what we want to do is graph the model. So you can graph the model using the ordered pairs that we only have one ordered pair at this time, or you can create a table, which it might be helpful and beneficial to actually have that table. So my parent function of my growth model is going to be based on, it's going to be 0, 1, 1, comma, my B value. So 0, 1, and 1, comma, my B value is actually going to be 0.79. That is my decay factor. In this case, we don't have a reflection because we're not multiplying by a negative number. And we do have a stretch, and that's going to come from 1,200. So I'm going to multiply all y values by 1,200. So I'm going to have 0, 1,200, and 1, comma, 0.79 times 1,200 is 948. We are not adding or subtracting anything, so we do not have a translation. But I also have one other ordered pair that we can use to plot, and that's going to be located at 2, 748.92. And that came from example letter B. That's where that ordered pair is. So I'm going to plot those ordered pairs in order for me to come up with a nice curve for me to work with, in order for me to answer letter D. So I'm going to plot 0, 1200, 1, 948, and 2, 748. Excuse me. All right. It looks like it's going to be decreasing like so. Right around here. All right. So now it says, estimate when the television will be around $300. All right, so that's what we want to do. We want to guess where is it going to be about $300. So I'm going to clean up my graph a little bit, kind of eliminate this part. Where is it going to be $300? Okay, so because our graphs are going to be kind of inaccurate, I'm going to say that $300 is going to be located somewhere in here. So it's either going to be located at maybe 4, 5, 6, or 7. So let's go ahead and plug and chug, essentially, is the best approach. So I'm going to go y is equal to 1200 times 0.79 to the third power and come up with a number. Y is equal to 1200 times 0.79 to the fourth power and come up with a number. I'm going to go y is equal to 1200 times 0.79 to the fifth power and come up with a number. And y is equal to 1200 times 0.79 to the sixth power, come up with a number, and I guess 7 is a part of that. So y is equal to 1200 times 0.79 to the seventh power. I'm going to, once I get to a number that's 300 or pretty close to 300, I'm going to stop. So I'm going to enter into my calculator all of my exponents, and it looks like at 0.7 or to the third power we have 591.65. And that's not anywhere close to 300, so that is out. So now I'm going to try to the fourth power, and I end up getting 467.4. So 467.4, which that's not anywhere close to 300, so that's not going to work. So now I'm going to try 5. And that's 369. That's kind of close. So that's $369.25. All right, that's pretty close. I'm not going to cross it out quite yet. So I'm going to try 6. And 6, I get 291.7. So that's 291.70. So now we've gone below 300. So we have to ask ourselves, which, I'm not even going to try 7. 7 is going to be way too low. So we have to ask ourselves which number is closer to $300, and in this case, 6 is closer, the exponent of 6, which means 6 years is closer to $300. So we're going to say, use the graph to estimate when the value of the television will be about $300 after about 6 years. The television will be worth approximately $300. And that is our answer. We have one last topic to talk about, and that deals with our graphs a little bit. And this topic is going to be very important, especially when we are doing our next lesson over the natural base functions. And it says when an exponent is raised to a negative power. So we're going to raise an exponential function to a negative power. This indicates a reflection. Now, anytime we've ever had a negative where we've been multiplying by a negative number, we've always had a reflection across the x-axis. But if the exponent is negative, that indicates that we have a reflection across the y-axis. And notice that our graph for exponential decay models was a reflection across the y-axis. So it may be written, the problem or the exponential function may be written with a positive exponent by simply changing the base of b to its reciprocal of 1 over b. So that's exactly what we're going to do for letter A and letter B. We're going to write each function with a positive exponent. So right now we have y is equal to 3 times 5 to the negative x power. So we're going to take our base and write the exponent, or the reciprocal of our base, excuse me. So what we want to do is, in the event that you have a negative exponent, you're going to write your base using a reciprocal. So we still have 3, but my base of 5 is going to be written with a reciprocal of 1 over 5 raised to the positive x power. Now before I go on to letter B, let me explain how this works and why this works. Otherwise you're going to be lost. So this is why this works. Number 1, we are starting with y is equal to 3 times 5 to the negative x power. What we know about negative exponents is that they can't be negative. You're not allowed to have a negative exponent. So I'm going to rewrite this as 3 times 5 over 1. And I'm going to raise this to the negative x power. And what I'm going to do is I'm going to distribute that negative exponent to each term. So I'm going to write this as 3 times 5 to the negative x power divided by 1 to the negative x power. Well, anything with a negative exponent is not happy where it's at. So 5 to the negative x will come down, and 1 to the negative x will come up. What now happens is that we have y equals 3 times 1 to the positive x power divided by 5 to the power, or to the positive x power. Since both of these two values or bases have the same exponent, we can factor out that exponent by rewriting it as y equals 3 times 1/5 to the x power. So what we're essentially doing is getting rid of the negative exponent by rewriting the base as its own reciprocal. So for letter B, the reciprocal of 1/3 is 3. So the reciprocal, or rewriting this using a positive exponent, we're going to have f of x is equal to -2 times 3 to the positive x power. And that's all that you'll do for those types of problems. So here's why it's important. We're going to have functions where you're going to see something like y is equal to a times b to the rx power. And that r represents a horizontal shrink or a horizontal stretch. So the r value indicates a horizontal shrink or stretch. For our cases and for our purposes, we're just going to be working with an r value that is positive or negative, but if we were to be working with an r value that was different, we would be multiplying all x values in our transformations table, when we would be multiplying all x values by 1 over r. We would be multiplying by the reciprocal. So whenever we've worked with anything next to x, we've always done the opposite of what we see. And so the opposite of multiplying by a regular r is to multiply by the reciprocal of r. But the most important thing about what I'm trying to say here is that if you see y is equal to a times b to the negative x power, what that negative part is going to indicate, so this negative right here is going to indicate a reflection across the y-axis. And that's what we're going to see in tomorrow's lesson, and the whole reason for why the graph is reflected in this lesson. If this was confusing for you, don't worry about it. We'll talk about it more in the next lesson. But in the meantime, we're going to stop right here. And this is the end of 7-2. If you have any questions, please make sure you let me know. Otherwise, I hope you have a wonderful day.